Hi, in this video I want to talk about velocity and acceleration in polar coordinates. Now usually when we discuss velocity and acceleration, two very important physical quantities when talking about motion of a particle, in that case we usually use the Cartesian coordinate frame of reference. However, sometimes if the motion is having some sort of a circular component associated with it, it's much beneficial to look at these physical quantities in some other coordinate frame of reference. Let's suppose polar coordinates. So polar coordinates is usually used for two-dimensional motion. Okay, so let me say that if the motion is two-dimensional, then instead of talking about the coordinates in x and y terminology, we can use some other terminology, and then that might be beneficial in problem solving. So let's first understand what the polar coordinates are, look at their transformation equations, and then I'll show you how to obtain the expressions for velocity and acceleration in those polar coordinates as opposed to Cartesian coordinates. Okay, so let's suppose that you are familiar with the Cartesian coordinates for two-dimensional motion, which is x, y. So if you have a point mass particle which is in motion, then if at a given point in time the point mass particle is at a point where the distances along the x-axis are given by x and the distances along the y-axis are given by y, then x and y simply are represented as the coordinates for this particular point where the particle is present in the Cartesian coordinates, right? However, in polar coordinates, this is not the system that we use. The system that we used is slightly different. Okay, so the system that we use is basically one number is the radial distance that we draw from the origin to that particular point, and the angular displacement from some reference axis, let's suppose the x-axis. So the angular displacement with respect to some reference axis is given by theta, and the radial distance from the origin of the coordinate frame of reference to that particular point is given by r. So that particular point, instead of being defined by x and y, is now defined by r and theta. So this is the polar coordinate. So instead of representing the point P in terms of x and y, we represent the point P in terms of r and theta, where r is the radial distance from the origin and theta is the angular displacement with respect to some reference axis. Now, before I look at the velocity and acceleration expressions, I can show the transformation equations and their relationship. So, as you can see from the diagram here, from a geometrical representation, what is the relationship between x, y and r and theta? And from the geometrical representation, I can say that x is simply equal to r cos theta and y is simply equal to r sin theta, right? So if you want to make a transition from the polar coordinates to the Cartesian coordinates, then you can quite simply use these two equations. However, what if you are interested in making the reverse transformation? You want to go from the Cartesian coordinates to the polar coordinates, then what can you use? Well, we can find out. First of all, I can say that let's suppose I take the square of both these two equations. Okay, so if I use x square is equal to r square cos square theta, first equation, and the second equation is y square is equal to r square sin square theta, and I add both of them together, then this simply gives me x square plus y square is equal to r square cos square theta plus r square sin square theta. So this simply becomes r square, inside brackets I can write sin square theta plus cos square theta. Now you automatically know that sin square theta plus cos square theta is nothing but what? It is equal to 1. So this simply becomes x square plus y square is equal to r square. Or I can also simplify this and say that r is simply equal to square root of x square plus y square. Now of course you cannot have negative because r is simply the distance from the origin to that particular point. Now next what I can do is I can divide both these two equations. So if I, let's suppose, divide y by x, okay, then I end up getting what? R sin theta upon r cos theta. Sin r gets cancelled and you're left with tan theta is equal to y upon x, or theta is equal to tan inverse of y upon x. So you finally get these two equations. The first equation is r is equal to square root of x square plus y square and theta is equal to tan inverse of x. So these are the reverse transformation equations if you are interested in making a transition from Cartesian coordinates to polar coordinates. Okay, so now that I have shown you the relationship between the Cartesian and the polar coordinates and these two frames of reference, I want to obtain different physical quantities in terms of this new coordinate system. So especially velocity, acceleration, and before that position vector. So to do that, let me again draw a similar kind of a diagram. Okay, so let's now look at this particular diagram. So let's suppose at the particular point in time the particle is here. So it has x and y components along the xy axis, but r and theta components in the polar frame of reference. So r is the radial distance between the origin and that particular point, and theta is the angular displacement between some reference axis and this radial vector that I have drawn here. Now, what are these? These are nothing but the unit vectors. So I cap is the unit vector in the x-axis, right? So I cap is in this particular direction, j cap is a unit vector in the y-axis. Now what are r cap and theta cap? So r cap is simply the unit vector along the direction of increasing r, okay, and theta cap is the unit vector along the direction of increasing theta, okay. So in the same way that I cap is the unit vector in the direction of increasing x, and j cap is a unit vector in the direction of increasing y, r cap here is a unit vector in the direction of increasing radial distance r, and theta cap is a unit vector in the direction of increasing polar angle theta. So the polar angle, as it increases, theta cap has this direction. So as you can see from here, r cap and theta cap are in perpendicular orientation. So basically r cap and theta cap are perpendicular to each other. You can see from this geometrical representation. Now, why have I shown in this particular manner? I have shown these unit vectors in these particular manner because this will help us in the transformation of the velocities and accelerations in the polar axis. So from the geometrical representation, we already know that all of these are unit vectors, right? So unit vector means that it has a magnitude of 1, it has a magnitude of 1, it has a magnitude of 1, it has a magnitude of 1. Now, if I look at the components of r and theta cap in terms of I cap and j cap, so let's suppose that I represent r cap onto the I cap axis. Alright, so if I represent this particular distance, then what is going to be this particular distance? Now this angle is theta, so this angle is also going to be equal to theta. So that means r cap cos theta. Now r cap has a magnitude of 1, so this is simply going to be equal to cos theta, right? Again, what about the component of r cap in the y-axis? Now r cap has a magnitude of 1, so this is theta, so this is simply nothing but sine theta, right? Similarly, if I look at the component of theta cap in the I and the j cap axis, so theta cap also has a magnitude of 1, and since this is theta, that means this is also equal to theta, right? And if this is equal to theta, then this is simply equal to pi by 2 minus theta. So if this is pi by 2 minus theta, it means that what is this distance is nothing but sine pi by 2 minus theta, which comes out to be cos theta. And what is this distance? This is nothing but cos pi by 2 minus theta, which is nothing but sine theta. So if I want to write a relationship between these unit vectors r cap and theta cap with respect to I cap and j cap, I can say that r cap is simply equal to 1, which is magnitude of r cap cos theta in the I cap direction, plus r cap sine theta. All right, so r cap magnitude has 1, so sine theta in the y-axis. Similarly, theta cap can be said that it is equal to, so this is the negative axis. All right, this is negative axis, so this is nothing but minus sine theta I cap plus cos theta j cap. All right, now these relationships are quite important. Why? Because this will help us in making the transformations of velocities and accelerations in a polar coordinate reference. So please make sure that you understand that these relationships are true from this kind of a geometrical representation. So let's suppose this is point number 1 and let's suppose this is point number 2. So if you have understood that these relationships are true from this geometrical relationship, I can proceed further. Okay. So let's proceed further to first define the position vector, because if I define the position vector, I can then start defining the velocities and accelerations. Okay, so in polar coordinates, the position vector is simply defined as r is equal to the radial distance r cap. That's it. This is the position vector in polar coordinates. Now I can show that this contains all the information about the position vector by just making a transformation to xy axis. That way you will see that this indeed is true. So if I make a transformation to the xy axis, how can I do that? I can simply show that r vector is equal to r. All right, what is r cap? R cap is from 1. I can just write cos theta I cap plus sin theta j cap. So this is equal to r cos theta I cap plus r sin theta j cap, right? Now what is r cos theta and r sin theta? I already obtained the transformation equations here. So r cos theta and r sin theta is nothing but x and y respectively. So this is nothing but r is equal to x I cap plus y j cap. So this is a position vector in Cartesian coordinates, and this is a position vector in polar coordinates. Now you may say that this looks like as if there is no theta cap component here. This is because r cap itself is dependent upon theta, right? Now as you can see here, as the particle keeps on moving, the directions of r cap and theta cap keep on changing. Now in the Cartesian frame, the directions of I cap and j cap do not change. They are constant no matter where the point is. The direction of I cap is always here, this direction. The direction of j cap is always in this direction. However, the directions of r and theta cap change for different points in space. So in a way, you can say that r cap here is basically a function of theta. So it contains all the information for the polar angle as well as the radial distance. As you can show that this equation is equivalent, or this representation of the position vector is equivalent to this representation of the position vector in polar coordinates. So now that I have defined position vector, I can go ahead and define the velocity vector. So what is the velocity vector? The velocity vector is nothing but the derivative of the position vector, right? So if r is this, then velocity vector is nothing but d by dt of r cap. Now this can be written as dr upon dt r cap plus r dr cap upon dt. Now in this case, dr cap upon dt is not equal to 0. Why? Because as the particle keeps on moving, its position changes, and I just now told you that for different points in the space in polar coordinates, r cap has different directions. So for this point, r cap has this direction, for some other point it will have different direction, and on and on. Therefore this particular quantity is non-zero. So here I can say that v is equal to dr upon dt, which I'll write as, let's suppose, the time derivative of r dot. Okay, r dot simply represents dr upon dt, r cap plus r into dr cap upon dt. Now how to find this particular quantity? So we can find this particular quantity from these expressions that we have obtained. So what do we know? We know that r cap is simply equal to cos theta I cap plus sin theta j cap, right? So if I do a time derivative of r cap, then this will simply lead to a time derivative of the right hand side, which is cos theta I cap plus sin theta j cap. So if I do a time derivative of cos theta, then again I will have to do a time derivative of theta. So this becomes theta minus sin theta I cap plus theta dot, and then again theta dot cos theta j caps. Okay, so time derivative of cos theta is minus sin theta, and then time derivative of theta is theta dot. So this is simply nothing but minus sin theta I cap plus cos theta j cap multiplied by theta dot. Now what is this quantity? If you remember, this is nothing but theta cap. Minus sin theta I cap plus cos theta j cap is theta cap. So this can simply be written as theta dot theta cap. So this is quite interesting. D upon dt of r cap is equal to theta dot, which is the time derivative of the angular displacement, which is nothing but omega. Okay, theta cap. Now this is quite interesting, okay, and we need to remember this. We'll use this for the case of acceleration also. So let's suppose this is which equation? Let's suppose this is equation number 3. Okay, now I can use this here. Okay, I can use this here. So I can use this here to obtain a fuller expression for velocity. So velocity is r dot r cap plus r theta dot theta cap. That's it. This is the velocity expression in terms of the polar coordinate system. Okay, so I can say that if a particle is in motion, all right, so if there a particle and the particle is in motion in some sort of a path, okay, and at a given particular point, the velocity will have different components. So it will have a component with respect to the increasing radial distance, so it will have a component in this direction. So that is nothing but this particular quantity, which I'll say as VR, and it will have a component along this particular direction, along the direction of theta cap. So that is nothing but v theta. So this is along r cap direction and this is along theta cap direction. So what I mean by this is that the velocity in the polar coordinates is nothing but vr r cap, the component along the r cap direction, and v theta theta cap, the component along the theta cap directions, where VR, as I have shown, is equal to r dot, also dr upon dt, and v theta is simply equal to r theta dot or r d theta upon dt. Now this is known as the radial velocity. Okay, so this is known as radial velocity or radial speed, and this quantity is known as transverse velocity. Okay, so this quantity is the radial velocity and this is either the tangential or the transverse velocity, which is how the velocity is represented in polar coordinates. Now, if I use this information to now obtain the acceleration in polar coordinates, then I can again start with the velocity expression. So what is the velocity expression that we just now obtained? Velocity is the r dot r cap plus r theta dot theta cap, right? This is the velocity expression that I just now obtained. Now what is acceleration? Acceleration is nothing but the time derivative of velocity. Okay, so dv upon dt, right? So if I do a time derivative of these quantities, r dot r cap plus r theta dot theta cap, now I need to write all of them in its individual terms. Okay, so d by dt of this will lead to two terms. So the first term is r double dot r cap, and the second term is r dot dr cap upon dt, right? Similarly, there are three terms here, so time derivative will lead to three terms. So the first is r dot theta cap, plus the second term is r theta double dot theta cap, and the last term is r theta dot d theta cap upon dt, right? Now we already know what dr cap upon dt is. We obtained it here, but we do not know what d theta cap upon dt is. This is also something that we need to obtain. So before I move ahead, let's suppose this is point number 4. Let's first obtain this particular quantity. How can you obtain that? We can obtain that from our equation here. So what is theta cap? Theta cap is minus sin theta I cap plus cos theta j cap. So if I do a time derivative of theta cap, this will simply give me minus cos theta multiplied by theta dot I cap plus minus theta dot sin theta j cap. So this is equal to minus of theta dot cos theta I cap plus sin theta j cap. Now what is cos theta I cap plus sin theta j cap? Again, it is this r cap unit vector. So this can be written as minus theta dot r cap. So d theta cap upon dt is simply equal to minus theta dot r cap. Again, this is an important relationship. Okay, this is a relationship which is quite important, and let me say that this is relationship number 5. So using relationship number 5 and relationship number 3 in relationship number 4, we can write this as the acceleration A is equal to r double dot r cap plus r dot theta cap plus r dot theta cap plus r theta double dot theta cap plus, no, it's minus, right, minus r theta dot into theta dot r cap. So writing properly, A is simply equal to r cap and r cap, these two quantities are common, so r double dot minus r theta dot square r cap plus r theta double dot plus 2 r dot theta cap. So this is finally the expression for the acceleration in polar coordinates. Okay, so this is the quantity of acceleration associated with the radial direction. This is the quantity of acceleration associated with the polar angle. All right. Now, what do these quantities mean? Well, first of all, what is r double dot? d2r upon dt2, right? What is this? This is nothing but the linear acceleration, which is in the radial direction. Okay, this happens due to the change in the speed or change in the radial speed of the particle. Now, what about this quantity? This quantity is nothing but r d2 theta upon dt2, right? This is nothing but the linear acceleration in the tangential direction. Okay, so this is the linear acceleration in the radial direction, so along the radial r cap direction, and this is the linear acceleration along the tangential direction, so in the direction of increasing theta. What about these other two quantities? Well, these are two interesting quantities. This quantity arises due to centripetal acceleration. So because the particle is experiencing some kind of a circular motion, the centripetal acceleration component along the r cap direction is this, and this arises because of the any kind of rotation involved, you end up getting what is known as Coriolis acceleration. Okay, so this is what the acceleration looks like. So finally, what I have done in this video is, quite simply put, I have shown that for a transformation from xy Cartesian coordinate to a polar r theta coordinates, you can use these transformation equations or these reverse transformation equations. Next, I showed the relationship between the unit vectors r theta and I cap j cap from this geometrical representation, and I showed how r cap and theta cap can be written in terms of I cap and j cap. Using these, I showed the position vector in polar coordinates can be written in this manner, and the velocity vector in polar coordinates can be written in this particular manner, where the velocity component in the r cap direction is the radial velocity and the velocity component in the theta cap direction is the transverse or the tangential velocity. Lastly, I obtained the acceleration in the polar coordinates, where it contains many terms. In the radial direction, you have the linear acceleration and the centripetal acceleration, or linear acceleration minus the centripetal acceleration, and in the tangential direction, you have the linear acceleration along tangential direction plus the Coriolis acceleration. So I hope you have understood how to obtain the acceleration, the velocity and the position vector in polar coordinates for a particle moving in 2 dimensions. So that's it for today. I hope you understood something from this video. Thank you very much.